Hi there, Nikki here, and welcome to another network automation video. In this video, I'm going to deploy BGP and OSPF across the routers and switches of my lab using Ansible with Jinja2 templates. But before we get into that, I just want to talk for a couple of minutes about my lab and how it's set up and what I intend to do in this particular video. So I still have my three sites, but what I've done is I've set as a seed value BGP 65000, and I've assigned a site number to each site 1, 2, and 3. So when we get to generating the config, we're going to use the seed value and add the site number to work out the BGP number for each of the sites. So site 1 will become 6500 plus 1, etc. for the other sites. And the other thing I wanted to just talk about is the importance of having standard config when it comes to standard predictable config across sites when it comes to network automation. So in this case, the routers in each site follow the same pattern, whereby gig 01 connects to core site router 1 and gig 02 connects to router 2, and the Ethernet 0 is the LAN interface to the switches, and likewise the switches follow the same pattern in each site, where 00 is router 1 and 01 is router 2. So most people do this anyway, but when it comes to network automation, this becomes really important, because if you're automating a large network and you know that they all follow this predictable layout, then you can confidently refer to variables such as iOS fact variables, the interface name to interrogate what the IP address is of a particular interface. And I'll show that in the videos. The other thing is all of these links are set up as point-to-point links with /30 subnets, and the way I've configured it is the core site always has the lower IP address in the subnet, so .1, .2, etc. And it's the same for the branch routers going down to the core switch. There's /30 subnets, and this would be a .1, .2, or the next subnet .5, .6, or whatever. And the target design that I'm going to deploy here is we're going to deploy OSPF on the switch enabled up to router 1 and 2 in each site, and then between the branch routers and the core site routers we're going to run eBGP. On the core site I will configure a default route pointing to null 0, advertise that into BGP, and then in these routers in the branches in OSPF, I'll configure a default information originate. So if a default route exists, it will advertise it down to the switch via OSPF. And what we hope when we deploy the config is that site 2 will be able to ping site 3. So I'm going to configure 3 VLANs in each site, VLAN 10, 20, and 30, and I'm going to verify that I can connect between these two sites, which will route via the core. So that's the lab. So if we go back to the Ansible host and just have a look at the directory layout. So again here I have a fact underscore cache.yaml playbook that simply caches facts from each of the hosts by setting gather facts to be true, and saves them into the fact cache directory, which contains a file for each of the devices in the lab. And as before, if we look at that file, we will see that say site 2 router 2, we'll see that all of the facts are there in JSON format, and as described in an earlier video, anywhere we have a brace, that signifies a dictionary, and anywhere we have a square bracket, that signifies a list. So by doing that, as discussed in previous videos, it just speeds up my playbooks. I don't have to gather facts every time I connect to a device. Also, what I have in here is a group vars directory for declaring global variables. So Ansible always checks for the existence of a group vars, and anything that's declared in that directory will be a variable that's available to all hosts. In this directory, I have a subdirectory called all. So again, Ansible will automatically detect if an all subdirectory exists in group vars, and if it does, it will include everything that's subsequently declared in that subdirectory. So we go into the all subdirectory, and in there is where I declare the VLANs. So if we just have a quick look at that, you'll see I have declared the VLANs in the 3 VLANs I discussed, 10, 20, 30. But because this is a YAML file, it declares lists and dictionaries differently. So like with all YAML files, we start with the 3 dashes, and each dash here tells us that that VLANs is a list, and each element of the list is a dictionary. So we have our key value pairs, ID 10 and name for the name of the VLAN, data, voice, wireless. So it's essentially VLANs is a list of 3 elements, and each element is a dictionary. And you'll see that when we interrogate this list in Jinja, we typically use a for loop, and we reference this VLANs in uppercase, which is automatically declared when Ansible runs, because it's in this group vars /all directory. And we can loop through each element and refer to these key value pairs, and we'll see that in the Jinja templates. So if we just go back to our main folder, the other thing I just wanted to show is the hosts file I modified to include a site ID. So for every router or switch in each site, I've declared the site ID for that device. So site 1, 2, and 3. And then, as I was saying, I'm going to use that variable to auto-generate the BGP number for each of the sites. And you'll see that also in the Jinja templates. The other thing as well is I've created an output directory. Currently it's empty, but when you see the playbook, you'll see that the first thing I do is, using the Jinja templates, I generate the config with the Ansible module called template. And when I generate the config, I need to save that in a directory on the Ansible host. So I save it in the output directory, and I'll give it a unique name per device by programming the inventory underscore host name, i.e. the host name of the device, into the name of the file. So we'll see that in a few minutes. And then once we have those configs generated in the output directory, we will use the iOS config Ansible module to take the config file and deploy that config to the router. So that's the purpose of the output directory. And then I've created a templates directory where I store all of my Jinja templates. So if we go into the templates directory, we will see that I have a separate Jinja template for my core routers, my branch switches, and also my branch routers, which I've I've split up, and I'll describe that in a few minutes. But if we just start off with the branch switches and have a look here, what we want to do is create the VLANs, create the SVIs, and configure OSPF. So as I was saying, with the VLANs list that we declared in group vars all in the file VLANs.yaml, a simple for loop allows us to interrogate each element of the list. So in Jinja, if you want to configure a conditional, whether it's a for loop or an if-else statement, you must enclose it in single brace percentage like I have done here. And then this for loop, what it does, as it iterates through each element, it takes the values that it's found, i.e. the dictionary, and it stores it in a temporary variable that I've just called I here. And then once I have that dictionary, I can configure the VLAN with your regular VLAN command that you would on a switch, and the variable is enclosed in double braces. So i.id is the VLAN ID, and i.name is the name that we assign to the VLAN, and it loops through each element, and we close the loop or close the for loop with the end for statement, also enclosed in the single brace percentage. Then this is just a regular interface range command. So we're configuring the interface on the switch that connects to router 1 and router 2 to be OSPF network type point to point, and to be placed in area 1 of OSPF process 100. And then to create the SVIs, we create another for loop, and through the VLANs list again, and similar to the previous for loop, we can refer to it the variable in double braces. So we configure interface VLAN, and then we have to configure an IP address. So to configure the IP address, I've used the site ID that was declared in the host inventory file. So I've programmed the site ID into the second octet and the VLAN number into the third octet, and the host is always .1. So if we're in site 2, it's going to be 10.2.10.1 for VLAN 10, or if it was site 3, it'll become 10.3.10.1, and the same with the other VLANs. So the SVIs also go into area 1 of our OSPF process, and we shut down. We do a no shut on the SVI. What was that? And then we close the for loop, and in the OSPF process we just configure passive interface default to ensure that OSPF neighborships are only formed on our interfaces up to our routers. So that's it for our branch switches. So then if we have a look, next I'm going to just look at the core routers. And in this one, I'm using the host vars method to refer to the facts that are stored in my fact cache. So here we are first of all configuring our router BGP process. So as I was saying before, I'm using 65000 as our seed value, and I just plus the site ID. So I'll get my BGP number, AS number for each site. So site 1, 65001, site 2, 65002, etc. I then have a if-else statement conditional. So when we get to the playbook, when I'm actually using or configuring the Jinja template, the playbook will be configured to only run it for the core routers, which I've declared as a group PE in my inventory file, my host file. So in my conditional, I need to determine if I'm looking at site 1, router 1 or router 2, because the BGP peers are going to be different. So I have an if statement here that goes if s1-1 in inventory underscore hostname, that global variable that refers to the hostname value in our inventory file, not what's configured on the switch. It may be the same, but what we have declared in the inventory file, the host file. And then I configure my neighbor statements. So for my neighbor statements here, what I do is for each of my neighbors, I use the host vars method to determine what their BGP peer IP address. So in this second one here, I'm looking at site 2 router 1 on Ethernet 0/1. So if I'm configuring this router here and I want to configure the BGP pair, what hostvar is doing is it's looking in my fact cache for this router here, looks at interface ETH01 and works out what its IP address is, and then we know what the neighbor IP address is in the BGP process for router 1, and we'll do that for each of router 1's pairs. So you can see that I do it for it's iBGP pairing to site 1 router 2, and then the 2 routers in site 2 and the 2 routers in site 3, and I configured the remote AS by doing a similar process to the router BGP process, in that I use a seed value of 65000, and then I used host vars for each of my routers to get its site ID and add that value on, and then I get the correct remote AS value. If this conditional fails, then it must be site 1 router 2. So we go into the else statement, and then it's the exact same. Use the fact cache Ansible underscore net interface to work out the pair IP address, etc. Then we go into address family IPv4, and we configure a network statement for 000, and down the bottom, after the BGP is configured, I configure a local static route for the default route to point to null 0. Then I again have an if else conditional to work out the neighbor IP address so that I can activate it. So this time it's the exact same as before, using host vars, and that's how we configure the core router, right? So for the branch routers, I decided to do it slightly different to show another method of determining what the pair IP address is. But also, these are the only devices that will have two routing processes: BGP up to the core and OSPF down to its local switch. So if you're automating routers and you have quite a long config, it can get quite cumbersome to manage that in one Jinja file. So you can actually break it up. So what I usually do is I break it up into different sections. So I would look at a full show run of a router, and I'd start at the top, and I might have, for instance, a AAA section for configuring AAA, and then an interface section, and then my routing protocol section, and then maybe my banner message section down the bottom. In this instance, what I've done is I've created an OSPF section and a BGP section, and they're in their own dedicated Jinja files, and they're collated in this branch routing.all file. So if we look at branch routing.all, it's just using the include command to include my two Jinja files. So when I reference these in the playbook that I'll show in a few minutes, I will never reference these two Jinja files directly, I will just call the branch routing.all file. So if we just look at each of these, so the OSPF one, branch routers OSPF, is really simple. I don't have any variables that I need to interrogate here. I know Ethernet 00 is always the router interface to the switch. I put it in the correct OSPF area, and then I configure my passive interface, so I only enable peerings to be allowed on that one interface. And I also configured the default information originate so that the default route will get advertised down to the switch. And then in the BGP one, I just want to demonstrate how we can actually, there's other ways to get the peer address in BGP, and this method is a little bit easier. We don't need to have a separate entry. We don't need to interrogate the host vars. We can just what I'm doing in this instance is I'm looking at each device's local interface. So we're now looking at the branch routers, and we know Ethernet 01 connects to the core router 1. So I know what, when I connect to the device, I can easily tell what its IP address is by referencing the fax variable Ansible net interface Ethernet 01 IPv4, which has a single element list .0 and address is the IP address. And then I can pipe that through a Python function called IPMath. And what this does is it takes an IP address as input and allows you to add or subtract a value. So I take the IP address of the branch router and I subtract -1, which gives me the IP address of the core router. So if we look at our diagram again, what we're doing is in this particular play, we're going to be going through our core routers. So we go to this core router, we grab this IP address, we subtract 1 from the IP address, and that gives us the IP address of the router here, and that gives us our peer IP. And then the other thing I want to mention about the IPMath is this is via the IP-ADDR filter, which is documented on the Ansible website. So if you go to Ansible, just Google Ansible IP-ADDR, you will see you'll be directed to here, and this is a Python package, the net ADDR package. So if you want to use that, you have to install it with the DNF package installer. So the command would be sudo dnf install python 3-net ADDR, and you can do -y. I've already installed it, but if you run that command, it will install this Python library, and it will allow you to reference these modules like IPMath in your Jinja template. But you can see there's lots of different things you can do with this Python library with IP addresses. So you can find addresses in a range. You can verify IPv4, IPv6, or in my instance, I'm just using the IPMath filter that just allows you to take pass an IP address into IPMath, and then add or subtract a particular value to get an IP address, a particular IP address that you're interested in, and it works for both IPv4 and IPv6. So continuing on with the Jinja template, We also configured the remote AS with the seed value as we did in the previous template to get the correct remote AS. And in the address family, I redistribute OSPF and I activate the neighbor doing this using the same method of the IP math -1, and that is our Jinja templates. So that's all the templates. So if we now move back up into our root directory, the YAML file that's going to generate the config and deploy the config for us, I've called gen_conf.yaml. So if we have a look at that, what I've done is I've split this playbook into 3 plays. So I have a play for the core routers, a play for the switches, so the hosts is using the group switches, and then a play for the branch routers using the group CE. Each of the plays does the same thing. It uses the template module to generate the config, and the template module takes a value of source to tell it where your templates are stored, so core_routers.j2, and a destination DEST to tell the module where you want to store the generated config. So as I was saying before, I'm going to store it in the output directory, and I'm going to give it a name that's unique to each router and switch. And I do that by just embedding the inventory_host name enclosed in double braces, as you would in a Jinja template, into the file name for the configuration. So in this case, it's .CRE_routing.conf. Once the template, the config is generated, I can then use the iOS config module, which also has a source option that allows you to select the config file for that you want to deploy, which is exactly the same as above with the inventory_host name. So if it's going through site 1 router 1, this will have a value s1_r1.CRE_routing.conf and apply that config to the router. And then if the config is applied successfully, this last statement here, save_when, is basically saying if you modified the config, save it. So that becomes a copy run start. The branch is the exact same, just different file names. It's .lan.conf, and we deploy it exactly the same way. And the branch routers, again, identical, just .br for branch_routing.conf. And that's the playbook, so 3 plays. So let's now run this, and we will be able to see what config it has generated and how the deployment went. So we just gen_conf. So we run this, and it goes through each of our plays. Okay, I have a error here. Right, I think what's happened here is my fact cache has expired. If you remember, Ansible CFG has a timeout value on my cache. So what I might just do is I'm going to remove all of these, and I will run my fact cache again. You could, of course, just gather the facts in each play, so you don't have to do this step, but I'm doing this so that the playbook will run faster. And also, if you were doing it on a real network and you were automating hundreds of devices, that might be worth considering doing. So fact cache. So let's just do this. So this just should populate my fact_cache directory again and reset that timer. Right, so there we go. And that's all of them. So fact underscore cache is repopulated. And let's try running our playbook again. Okay, so we generate the config. And so that task there is now saved. The config for those two devices, router 1 and 2 and site 1, into the output directory. iOS config has deployed the config to the routers, and we do the same for the LAN switches. Deploy the config. And finally for the branch routers. So that's all the routers, and hopefully it'll deploy okay. And we're done. So we can see the recap at the end. All our devices were reachable, and the changed parameter here is saying that we applied changes to all of our routers. So if we now go into the output folder, we're going to have a file for each of the router types, or routers and switches rather, with the inventory underscore host name embedded into the file name. So if we just look at that first one there, so site1 dash router 1, so we can see the config that we created. So the 65000 plus 1 gives us our BGP number, and all of our neighbor statements with the correct remote BGP AS numbers. We going to advertise network quad 0, activate our BGP numbers, and create our default route. And if we just look at one of the other ones, say site 2 R1, similar, we create our BGP. Sorry, where am I? This one down here, sorry. So our interface Ethernet 0, which is our router interface down for switch, is put into the correct OSPF area. Our passive interface is configured, default information origination or OSPF process. Our BGP is configured in the correct AS, which is 2 for site 2. On our two neighbors are site 1 router 1 and router 2, so 65001, and we activate our BGP peerings and redistribute OSPF. And if we just finally look at one of our switches, so sorry, what are the switches again? So say site 2, so more site 2 dash switch. So here you can see we iterated through our VLANs, and we configured our VLAN 10 with its name, VLAN 20 and 30. We used interface range to configure our uplinks to our local routers into the correct OSPF area. We created our SVIs with the site ID embedded into the IP address, and the VLAN embedded into the IP address, so VLAN 10, 20, 30, and put into the OSPF area 1. And we make sure that we no shut those SVIs, and we configure our OSPF process similar to the other devices. So that is our config. So if we now go back to our lab and we just check site 1, router 1, then we should see BGP is configured. So there's the BGP that we just described, configured, and our default route to null 0 is configured. And if we just have a look at our BGP table, we can see that all of our pairs are up and we're receiving prefixes. So our route table should have some BGP learned prefixes. So we can see site 3's VLAN 10 2030 and site 2's VLAN 10 2030 are in the table. If we look at site 1, two BGP pairs, learning routes, and we should be learning a default route via BGP via our site 1, router 1. And then finally, if we connect into our switch, we should have OSPF neighbors, two neighbors, to router 1 and router 2 in the branch, and we should then also have hopefully learned a default route. So that's the default information originate that we've learned from both of our routers. And at this point, if we were to ping, so if we look at VLAN 10, this is 10.2.10.1, so we should, if everything is working, be able to ping 10.3.10.1, and we just source it off VLAN 10. We should be able to ping 20 and 30. So we've deployed our full config and we verified it. In another video, I'll actually automate the tests as well, and we can include a play at the end or in a separate playbook verification. Make sure that my BGP peers are up, make sure I can ping from one side to the other. That all can be automated as well, which I think is very important, that when you're automating, that you include automated tests, so you're getting feedback from Ansible that what you intended to configure has been configured successfully. So that's the config deployed for BGP and OSPF using Ansible with Jinja2 templates. But the last thing I just wanted to talk about is the concept of idempotency. So what that means is that when Ansible tries to connect to a device and it has been given a task to apply a particular configuration, it will look at one of the first things it will do is grab a show run, and it will compare line by line the config that you present to it, and if it finds a line that's already configured, it won't try and configure it again. And that can be really important if you're using Ansible to configure a large production network, and the config that you are applying is going to cause a routing protocol to bounce or some sort of state change. With idempotency, if the config you're trying to apply has already been applied, you're not going to unnecessarily cause an outage in your network. So that's built into Ansible. But Ansible doesn't know anything about configuring Cisco. It's doing very rudimentary compare what you're doing with a show run. So it's a text comparison. It doesn't know about how Cisco iOS is configured with address family IPv4 is inside router BGP. It just does that simple diff between what you're presenting and what's already out there. So that's another reason why indentation is really, really important. So I just wanted to demonstrate this as a wrap up in the video. So if we were to run our playbook again, we would expect that because we've already configured anything, it shouldn't do it again. And I want to show you why that's not always the case. So if we just run this just again, and you will see that anytime we get this in green, it means it's not running it again. It's realized I've already done this, I don't need to do it again. And anytime it's displayed in white, it's actually applying some config. So you will see here that the switches, for some reason, are getting config applied again. So we let that finish out. And this time, the only devices that got changed set to be greater than 0 is the 2 switches. And the reason for that is if we have a look at our template, which is branch switches, if you remember, I'm using the interface range command. But if you log into a switch, you will never see this in the running config. You will see interface gigabit 00 and interface gigabit 01. So if we had if we hadn't used interface range, if we had just used the regular interfaces, it would have, Ansible would have detected that in the diff it does when it connects into the box, and that's why config is getting reapplied with the 2 switches, but not with the routers. But if we were to just modify one of our scripts, I can just show you how important the indentation is. So if we were to just go into branch, no, let's do it with the core, be easier. If you can see here, I have indented address family IPv4. So if we go up to the top, you'll see in the very first space it begins router 1, and then indent in 1 space is where BGP is, and the exact same with address family. But if I was to bring address family IPv4 back to be level with the R of router BGP, then the indentation is wrong. And while if we got a config and the indentation was like that, and we just pasted it into a router, the router would happily accept it and configure it. But because Ansible doesn't know anything about Cisco iOS, it's just doing this very simple diff, this indentation becomes really, really important. So if we just save that, and then if I run my playbook again and see what happens. So the first one is the core routers. So again, we generate, and this time it's changed something, so something's different. So there's 1 space out, but it's bombed out. And what's actually happened is, if you look at this error message here, you'll see that the error was, if you just follow this, you'll see, where can I see it? Oh yeah, here's an example of it. Invalid input detected at. So as you know, in Cisco iOS, if you put in something iOS doesn't detect, it will throw you up the invalid input detected at error message. And you can see here it's because of address family IPv4. So what's actually happened is, because that indent is missing, Ansible thinks, okay, I need to apply the config address family IPv4, and it doesn't have any context of that is part of router BGP process. It tries to apply it in global configuration mode, which of course is going to fail, and that's why we get this error message. And this causes the playbook to fail, and it fails at that point and doesn't carry out any other plays or tasks. So that's just wanted to highlight how idempotency works. And if we just finally go into the output folder and grep the generator config, which would be say like site1, say r2 dot core, just to show you that router BGP and address family IPv4 are now incorrectly aligned, while if we compare that to what we were doing previously, which we would still have in one of the branch routers, you will see that the address family is, oh sorry, I'm looking at the wrong one. The address family is indented by one space, so it's aligned with BGP log neighbor changes, not router BGP. So watch out for that. That's really important. The other thing as well is if you have a no shut in your Jinja template, that can also cause idempotency to fail, because no shut never appears in your running config. So the way that you may address that is you have one play that generates and deploys all your config, and then a separate play that simply goes in and does your no shuts, and that ensures that in your first play you're protected by the built-in idempotency capability of Ansible. So that's one of my longer videos, and that wraps that up. So thank you very much, and I hope that was of some use.